And our first speaker, Hynek Schlawack, C Python and Twisted Core developer and BSF member. Okay, Hynek.
Oh, thank you. It's an honor to open here after such an impressive speech. Quick poll. Who knows the difference between SSL and TLS? Okay, you're in the right room. Okay, so, привет, I'm Hynek. This is how I look on the internet. When I'm not angry on Twitter or writing open source software, I'm doing infrastructure at a small but friendly German web hosting company. That is about it. I'm not here to talk about myself. I'm here to tell you that those shiny block icons, and I don't see my notes. Can someone who speaks Russian help me to see my notes? Awesome. This is great when you don't have your own computer. Okay. I needed something. So, they are a lie. So, why? You're never really safe. And while this statement may have been a bit controversial, like a year ago before Snowden, before Heartbleed, I can assure you that the state of the matters was just the same 1 year ago, 2 years ago, and even 10 years ago. Because all the problems that are surfacing now are much older, but nobody cared. That's a problem. Today, more than ever, you need to know how things fit together in order to assess and minimize risks. So, because you can do much more damage than any bug or any state agency will ever do if you do some very common mistakes. So, before we go out first step, this is the only link you have to write down. There will be no other links, there will be nothing else. I just want you to concentrate on what I'm saying, and afterwards you can revisit everything I've been saying. Especially, there's additional material to dive deeper into the concept I'm introducing, because 45 minutes is very little time for a topic like TLS. So, let's get started. Why is the state of SSL sorry? And let's start at the beginning and discuss what SSL actually is. So, what is SSL? And what the hell to do with TLS? And I think let's start with a history lesson, because everybody loves history lessons. And this one starts in the mid-90s, when Netscape started thinking it would be really nice that if you enter your credit card on the internet, it doesn't automatically mean that people start buying drugs out of your pocket. So, in 1995, they released a complete host SSL2 as the foundation for HTTPS. So the S stands for secure, not for SSL. 1 year later, they fixed the worst mistakes in SSL3, which is still commonly deployed, by the way. And 3 more years later, it finally became an official IETF standard and was renamed to TLS. So, to sum it up, SSL is a Netscape product from 1996. TLS is an official internet standard for 15 years now. So, basically, the name of my talk is wrong. But I just wanted to reach everybody, because still many people don't really know what TLS is, or they conflate it with Start TLS, which is something very different. And yeah, alliterations are always awesome, so it just works better for a title. So, if I had to trick you in here with the name, I hope you learned a few things today and will not say SSL in the future, because it totally irks me. In 2006 and 2008, the back then largely ignored TLS 1.1 and 1.2 have been released. Both fixed a lot of important things and added very nice features, but nobody cared. Fast forward last year. For some completely random reason, people started scrutinizing our security habits again, and what they found was not good at all. Quite the opposite. So, for example, all mainstream browsers supported only TLS1 until last year. TLS1 from 1999. We have been stuck in the 90s with our cryptography because nobody cared for 14 years. And Last year everything changed basically. The times where I'm using SSL or TLS was enough are gone. And it makes me more suspicious and reassured if some software claims that, because you really need to know what you're doing, because this technology has really sharp edges and the consequences can be very grave. So, let's start again. What is TLS? What does it want to provide you with? So first, there's peer identity. I'm pretty sure you all already heard of certificates. This is what's going on here. You prove that, or the server proves to the client usually, that it is who it claims to be. It protects you, therefore, from man-in-the-middle attacks or MITMs. It gives you confidentiality, which basically means encryption. That's what most people think of when they speak about TLS, that is now cryptography. Eavesdroppers cannot read the clear text of your conversations. And finally, it gives you message integrity. It ensures that you can detect if TLS records arrive mangled, out of order, multiple times, or not at all. So, now we've known what roughly you're provided with. Let's see how to use these all together, and we will discuss further details along the way. So, after this part, you will know the worst and smells of TLS deployments and what to avoid. And we'll start with servers. Unless noted, I'm sticking to OpenSSL from now on, because unless you're on Windows, that's most likely what you'll be using whether you like it or not. So, if you deploy server software, it's your duty to do it in as secure as possible way, because users can neither introspect nor affect your setup. So the first step is to use at least halfway up-to-date software. And if you're deploying anything older than what's in this slide now is, then you are being negligent, lazy, and should stop doing so immediately. And I'm generously assuming that you are using security backports, because if you don't, there's obviously no way that you are deploying anything older than 1.0.1G, because the heart and the bleeding and yes. So, get yourself up to date. This is the minimum feature baseline you need to get a halfway up secure TLS setup. Everything older is just wrong. So, the first thing you do when a client connects to your server is you provide them a certificate that says who you are, kind of an ID. So in order to make the client actually trust the certificate, it has to be signed by a trusted third party, a so-called certificate authority or CA. The set of public keys of those trusted third parties or CAs is what we call the trust database. And to prove that the certificate is actually yours because you're sending out to everybody, a secret key belongs to the certificate. So this one is then used for signatures, which in turn can be verified using the certificate. So that proves that you are in a possession of the secret key, however it came into your possession. So, there are various types of certificates right now. It depends on how much work the CA put into verifying who you are. So the simplest one is that they just check that you gave them money and that you're in possession of the DNS. And those you can get them for free if you look good enough. On the other side of the spectrum is extended validation. You maybe have already seen it somewhere. It basically means you give them a lot more money, the certificate is valid for a shorter time, and the CAs are happy to be mortgaged. So, and that's all there is to know. Information about validity plus signature from a trusted third party is a certificate. Your job now is to make sure that your certificate setup is trustworthy. Because TLS is more or less worthless if the clients that are connecting to you cannot verify who you are. And in practice, you will usually not get a certificate that is signed directly by a trusted third party. You will get a whole chain of certificates. And for example, in this example, this is from my homepage, there is one trusted CA at the very bottom, which is in a trust store. So this one is known to the client. And this one signed some Komodo certificate, which in turn signed some other Komodo certificate, which finally signed my certificate. So this is the chain, and if a client connects to the server, these 3 certificates are sent out. And it's pretty much the most common rookie mistake people do, that they forget to configure their servers to send out a chain along with their certificate. So take care of the chain. Make sure the certificate is valid for the host name of your server. And of course, make sure your certificates are not expired. Then all the little housekeeping, like disabling SSL 2.0, which should not be necessary nowadays. However, Apple's OpenSSL still ships with SSL 2, which I think is the only OpenSSL you can get nowadays. Somewhere which still supports SSL 2. Not that I'm suggesting you should deploy anything servery on OS X, which you should not. And if you don't have to support Windows XP, which is a luxury I don't have, you should also disable SSL 3. That's about it. Then disable TLS compressions. You might have heard of the crime attack, and that's it. The next objective is to configure your CIPHER suite such that each client gets the best possible encryption. So a CIPHER suite is just a tuple of various cryptographic primitives that are used together to secure the connection. And ultimately, you, the server, have the last say which ones are used, so you should use this power for good. And the CIPHER is by itself the most easy one to explain, so we'll start with that. You can imagine that as a black box, which gets the plaintext and a secret key as input, and it returns the ciphertext, which should be indistinguishable from random data as output. The other ciphers are symmetric, which is an important property. So if you want to decipher the ciphertext to plaintext, you will need the exact same key again. I will talk about it more later. Other than that, this is pretty straightforward. This is the easy part. It gets more complicated because most ciphers nowadays are block-oriented, which means they work on a certain amount of data, and you can't just pass in a 1 GB move into it and wait to the ciphertext to come out on the other side. If the data exceeds the block size, which nowadays is usually 128 bits, you have to chop it up. If it's smaller, you have to pad it, so in practice you usually have to do both. And the most common way nowadays is still cipher block chaining, which by itself is totally fine, except it was implemented poorly in TLS, which bestowed us with a wide variety of mode-based attacks like Beast, which was fixed by TLS 1.1, by the way, which nobody used because nobody cared. So, other alternatives. There's, of course, client-side fixes. That's what browsers are doing for years now, and stream ciphers. In the past, people really like to use RC4. I will talk about it more. And in the future, we will hopefully be using CHA-20 to get rid of these problems. And finally, TLS 1.2 brought a completely new mode, which does much more than just chopping and padding, the so-called Galois counter mode, and I will be talking about it more later too. So, now we know what a cipher is, which one to use. You can spend a week on the internet to discuss with people which ciphers are the best. I'm just going to copy what basically Google is doing and what some other security researchers are recommending. So I'm just going to go out and say AES 128 GCM is probably the best thing you can have nowadays. There's a second one which is just as good, if not even better, and it's CHA-20 from Dan Bernstein. Now, AES in GCM is really good in hardware, while CHA is really good in software. So ideally you would support both and let the client decide what to use. And it's exactly what Google is doing, but it's not available to us mere mortals, so AES GCM it is. Even for the latest Safari and IE browsers, you will have to fall back to AES CPC, which is, again, is the same cipher, it's a different block mode. It's perfectly fine on TLS 1.1 and 1.2. Therefore, it's also safe to use as your only cipher if you don't trust Intel with their AES commands. So you can go for it too. The only problem is TLS 1, where CPC, as already said, is a problem. But you can do really much there because you have to support it anyway. So just pray that the the clients are fixed. And yeah. If you need to support some older operating systems and stacks, most notably Windows XP, you can use triple-DES. Triple-DES is a pretty secure cipher. It's just really slow because the 3 in DES means that the DES cipher is applied 3 times. So you can imagine that's not the most effective way to do crypto. And that's it. You don't need anything more to support everything you will encounter on the net. And be especially wary of the following ones. Export ciphers. They come, I think, from the 80s and early 90s when the cryptography exports from the United States were restricted. They are designed as backdoors, so avoid them at all costs. DES is still active in many old SSL stacks. It has 56-bit keys. You can brute force it probably on your phone. Don't use it either. And finally, RC4 is a bit more complicated. Well, actually, it's not really complicated. Cryptographers have been hinting for years that RC4 has some really, really bad properties and biases. People didn't really care, but Mr. Applebaum has access to the Snowden files, so I would take this seriously. And it was already last November when he said that. So, based on what I've heard from people who are both smarter and better informed than I am, I strongly discourage from using RC4 if you care about state agencies. So, going on. In order to encrypt and decrypt, you need a key. And as we said, the ciphers are symmetric, so you need the same key for encryption and decryption. And so you have to agree on keys for your encryption over an unencrypted channel, which kind of sounds like a chicken-egg problem. But fortunately, math came to the rescue and provides us with several ways to agree on keys without leaking them. And 3 of them are currently widely deployed. The unfortunately still most common one is RSA, which is not just a company who took a lot of money from the NSA, but also a public crypto system. So simple, you have a public key and a secret key, you encrypt the public key, you decrypt the secret key. Easy. The problem with RSA for key exchange though is that when the key bleeds out of the server, all future and past communications become plaintext to the attacker. Because it lacks perfect forward secrecy or that it's not PFS. And this bears repeating because one court order, one CVE, or one successful server break-in, and the attacker can really decipher everything they've ever captured, everything they capture, and everything that they will ever capture, and you have no way to know about that. And there are rumors that the NSA does have a database of RSA keys. So, ephemeral Diffie-Hellman is PFS, but it's slow. That's the reason why nobody used it in the past, although it has been around for quite a while. And the performance argument got moved with ECDHE, which is the elliptic curve version of DHE, which is both PFS and fast. And I cannot stress enough that you should do everything humanly possible to ensure perfect forward secrecy for as many users as possible. And for that you will require both DHE and ECDHE, and since ECDHE is faster, I suggest you prefer it. So, the last part is message authentication codes, which are used for integrity. Messages in TLS context just means it's a TLS record. It's a lump of data that got encrypted, sent out, received, unencrypted. Megs are not TLS specific, so don't let the word message confuse you in any way. They combine magic cryptodust with shared secret keys to ensure both the integrity and authenticity of messages. So, if you have a message, you know that it was sent by the or a person who also knows the secret key in that order. And TLS traditionally uses HMAGs for that, which are the keyed hash mags. Before that, SSL used something very similar but different. And if your connection is secured with a traditional cipher which uses an external HMAC, you can also configure which hashing function is used for this HMAC. And there isn't really anything imminent dangerous what you can do wrong. However, I like to disable MD5 hashes because they irk me. MD5 HMACs don't suffer from the same problems pure MD5 suffers, but come on, it's MD5. So, TLS 1.2 again, it introduced the possibility that ciphers bring their own MAC with them. And that's where the aforementioned Galant counter mode shines, because it integrates the block mode with the message authentication, so it's one step. So it's implemented efficiently in hardware, it's fast, it's nice, at least in theory. So, that's about it. And but you should make sure that you have the last word, because if you don't support only strong PFS ciphers, you don't, the best configuration, the best TLS implementations don't help you anything if there's a client, for some random reason, sends you a bad cipher at a own priority list on the top, and you comply, although you both could have had ECDH eCharger20. So, and at that point you're done. If you do everything I've said before, you're pretty fine, you're way off the average. However, thinking about it right, means unfortunately absolutely nothing. You have to test your results, because there are still a lot of problems that you can try to win. For example, RHEL and CentOS 6.5 both ship an OpenSSL that supports ECDHE. So, if you ask OpenSSL, do you do ECDHE, it says, yeah. But their Nginx is still compiled against the old OpenSSL, which does not. So it does not expose the new modern ciphers to the outside, which you will not know if you don't test it from the outside. If your server is HTTPS, which I'm going to assume is the most common case, it's a lucky day because there is a nice tool for it, the Qualys SSL server test. And again, it's a pretty common case, so I'm just going to show you how to read its output using the results of my homepage. I would like to stress that they test many more things that I'm going to enumerate here. So after you've done the basic stuff I'm talking about, you should go back and get everything green. Because an A+ is not that difficult, and it's worth it. So, the certificate. This is the certificate for my homepage. Not that I would need a HTTPS on my homepage, but I needed a good example, so I got a certificate for it. It's valid for my hostname with and without W. It's valid from last March until next May. It's a 4K RSA key. So this RSA key means something different than in a key exchange. It just means it uses RSA for signatures, which is the same algorithm, but it has different implications. So, as for RSA keys, 4K is the current state of the art, 2K is the common barely enough standard, and 1K is considered a security problem. Other alternatives would be DSS, which nobody uses, and ECDSA, which is gaining some traction, but is still widely under-supported by both clients and CAs. So if you want to deploy ECDSA, you have to find first a CA that will sign it for you, which is pretty difficult, and then they are taking a hefty premium for doing that for you. And then you have to do a dual certificate setup. And again, that's what Google is doing. It's not really feasible to normal people like us. So, the issuer is Komodo, and assigned a certificate using SHA-2, which is pretty nice. It's not very common yet, but it's coming up. It has no extended validation because it's a racket, and it's not really well tested, it's trusted, which is nice. So, protocols. Always make sure the TLS 1.2 or 1.1 are active, and SSL2 inactive. In the mid-grounds, it depends of the burden you are carrying. So, again, if you have to support Windows XP, you will have to have SSL3 on like we do. So, now back to Cypher Suites. This is the maybe less known notation used by the IETF in RFCs. OpenSSL uses something slightly different, but you will recognize all the same parts. And this is basically the CIPHER I'm suggesting. Let's take it apart. So it uses ECDHE for key exchange. It's fast and perfectly secure. It uses RSA for signatures, which I cannot configure. That's really derived from the type of my certificate. AES, already AGCM for encryption, and finally SHA-256 for key derivation on handshake. Again, if I would have been using a normal CIPHER, for example, this one here, this is using the SHA-256 also for the HMAX, but in this case not. And as you can see, the server strongly prefers PFS ciphers, so you can see ECDHE, DHE over non-PFS ones. Again, backward compatibility, again, Windows XP. You may see a pattern here. But this is a bit of a privileged view about web servers and browsers. There's still a lot of really shitty software out there, so if you're maintaining mail servers, you would wonder what's still out there. So your mileage may vary, you will have to test it for yourself, but you can accept it or not. And we'll talk about writing client software next. And it turns out that browsers aside, the client side of TLS is in the first check of them all. Which is kind of surprising because they have only one job: verify. Verify that the certificate the server sends you. Is it valid or is it expired? Does the trust chain validate? And finally, is the certificate valid for the hostname you wanted to connect for? Especially hostname verification is in such a pathetic state that there's even a scientific paper about how people don't verify the host names. And spoiler alert, Python is featured there too. So, unfortunately, OpenSSL is not really innocent of the situation. We will start with trust chain. It's opt-in, which is bad by itself. So, and you have to tell OpenSSL explicitly which CAs you trust, which is nice if you want to do certificate pinning, which is a nice thing, but usually that's not what you want to happen by default. So you have to read out your CI trust databases, which of course is highly platform dependent, so every OS has it elsewhere. Fortunately for you, there is a function that will, on properly configured systems, read the default trusted CAs from compiled path. For some random reason, this function is completely undocumented. So it appears at some spots on the web, and I had to read the source code to it to find out what it's actually doing. But this is what you want if you are using a Unix-based system, because it will use only file and directory-based trust databases, which is a problem because that means it does not work on Windows and Windows on OS 10. So, but OpenSSL is not the only one who's trying to make our life harder. So we have a nice function to load the trust database automatically. However, our nice vendors don't install them by default in many cases. So for FreeBSD, you have to install CA root analysis. On Debian and Red Hat, we have some consistency in both cases for CA certificates. And now it gets more complicated. On OS 10, Apple's shipping a really, really old OpenSSL, and they patched in their trust evaluation agent. I would strongly discourage of using it, because first it's old, and second it behaves in very unpredictable ways. So it cost me like 2 weeks to figure out what actually is going on in the TIA and why things don't work like they should. The alternative is homebrew or anything like that. In this case, it does something pretty clever. On installation, it creates a copy of the system trust store and uses that henceforth. So it's not perfect, but it's good as it gets. For Windows, there's the WinSubStore module on PyPI. And if you want to just completely bail on this whole problematic, just use Certify from PyPI. That's the packaged trust source from Mozilla, which they are using themselves. And then you don't have to cope with the whole platform dependency things. So, let's get really sad. Talk about hostname verification. The problem here is that OpenSSL basically just tells the developers this. There's absolutely no assistance from OpenSSL whatsoever to verify whether a certificate is valid for a host name. And there's not even any documentation on that. And it should be noted that the wiki of OpenSSL uses a self-signed certificate. So, what does it mean? That either people are not verifying host names, which they don't, or that they have to implement it themselves using RFCs and bogus advice from Stack Overflow, which they do too. And what happens next? CVEs. It's running security bugs. And Python is one of them too, so we've been bit by that too. Yeah, so, however, if you don't verify your trust chain or the host names, you are super susceptible to man-in-the-middle attacks. So, if you don't verify certificates at all, which is the default behavior, I can be your Google with a self-signed certificate I can create in 5 seconds. If you verify the certificate, but don't verify the host name, I can still be your Google, I just have to use the certificate of my own homepage, which is perfectly trustworthy, just not for the host name, but you won't know because you didn't look. So, verify all the things. If there's only one thing you're taking from this talk, it's please verify, check the software you are using, verifies host names, check the libraries that are using that are verifying host names, because most don't. So, other than that, everything else is mundane. Limit to acceptable ciphers to strong ones for times of connecting to poorly configured servers, which is most of the time, and disable SSL too. That's it. That's all, and yet so very few do it. It's a perfect storm of ignorance on one side, and OpenSSL and operating system vendors making it unnecessarily hard for us. So, and we'll finish with the weakest link of the security chain, the users. Because they can make everything fall apart, no matter how hard the rest tries to keep them safe. And it starts usually with fundamental misconceptions about what TLS can or even wants to do for you. So, for example, it's nice that your connection to your to your mail server or to your chat server is secured with the latest and greatest cipher. It's awesome, keep doing it. Otherwise, people will steal your password. However, if the other side, if the other person you're communicating with is connected using plaintext or some intermediate server is compromised, the security of this conversation, the confidentiality of this conversation is 0. And you can't know if something of that is happening. There is no feedback to you. So you have to always assume the worst. You will need some end-to-end protocol like PGP for email or OTR for chat if you really need confidentiality in the conversation. It's not between 2 direct peers. And then there's the problem that certain data simply cannot be encrypted. So if you're surfing a job site at work using HTTPS, your IT department will still know because your DNS queries will give you away, your traffic patterns will give you away. If they really want to, they can even find out on what pages you have been, because metadata can be really, really treacherous. So in this case, you will need a VPN. However, a VPN routes all your traffic through their own networks. You better make sure that you trust them. And this applies even worse to content delivery networks, because they see your data even unencrypted. Because why? They're doing the TLS termination for you. Maybe they are communicating with your backend via TLS too, but still, the termination to the front end is done by them. So, Fastly can sniff all your API passwords if they wanted to. So, this is another important reason to never reuse passwords, because you never know how many third parties are gonna see it. You just can't know. So, if you've ever clicked away something like this, you may have been MIT ranked. And the rule is pretty simple. Investigate the warning and use your best judgment. So for example, if the certificate is fine but expired 5 minutes ago, You can tweet something snarky and be done with it. You're probably safe. If just part of the hostname mismatches and you know the background, maybe it's twisted, still doesn't support SNI properly in 2014, you're probably fine too. But other than that, if you don't know what's going on, if you don't 100% understand the problem, you should never proceed. Because MIT MADEX are really easy on public networks, like airports, conferences, your favorite hipster cafe. All it takes is a rogue HTTP server. And the next level of clicking mindlessly is if some crook tricks you into installing their root certificate into your trust database. Because that basically means that in the future, any MITM using a certificate that is signed by this root certificate will not be warned against it because it's trustworthy. So this is probably the worst case that can happen. And people install root certificates all the time, especially on their phones when they install these profiles. That's basically nothing else than this, or it can be. So speaking of trust databases, even if the user doesn't screw up, there's still a lot that can go wrong. And so a trust database, quick reminder, is the database of all CAs that are trustworthy. And if you connect somewhere, you check whether the chain is terminated by something in there. So the problem is that this database usually contains CAs which may cause some discomfort to you. So in this case, the US Department of Defense can assign any certificate they want for any hostname they want, and you will always have just a green little lock in your navbar. And it's not like China is standing back or Russia. Every country has some CA they can subvert. You are not safe from this. And it's not unheard of that CAs got hacked, make really bad mistakes, are forced to cooperate, or they are just big corporations which may have very different priorities than you have. So, for example, Google and Microsoft can both issue certificates, whatever you make up from it, but it's still a problem. So this trust problem that is centralized and you have no control over is just broken. And speaking of broken, we will talk about Python now. And the rule of the thumb is pretty simple. Don't do TLS in Python yourself if you can help it. And let battle-tested software do that for you. For example, if you're doing web applications, there isn't really a reason for you to take care of the TLS on the server side yourself. Properly configured Nginx or Apache will save you a lot of grief. So there's a lot of documentation on the web how to get it properly, and that's simply not true for some random module on PyPI. We just added TLS because someone asked for it on our plug. So, but life usually isn't that simple. So let's get our hands dirty anyway. The Python TLS landscape basically consists of two camps: the standard library and PyOpenSSL. I will start with the standard library, and it's terrible. It started being less terrible with 3.3, but up until then it's terrible. And even in the latest 3.4, because of backward compatibility reasons, the defaults are still absolutely horrendous. So there is all the code they need for hostname verification, but it's not used by default because some core developers argue that people are running broken software and we must not unbreak our software because it would break their broken software. So, but this is still a situation you will push for on Python 2 because this is just plain broken. It's missing very important part of the OpenSSL API, so you cannot write forward secure server. You can't. So, in other words, you should never write TLS servers with Python 2's standard library. You cannot set certain options because, again, the APIs aren't there. So you cannot switch off SSL2, you cannot switch off TLS encryption, TLS compression. And finally, the OpenSSL you're using from within Python is the one Python has been compiled against. So if you want a newer one, you have to recompile all your chain. And yeah. So again, hosting verification is a big problem too. It has been added in 3.2, but that doesn't really help you probably. There is a backport on PyPI, which is fortunate, but I don't know how many of you knew about that and used it, but it's a double opt-in, and it's a bit problematic, I dare say. So, switching to PyOpenSSL. PyOpenSSL comes from a time where the standard library SSL module was even burst or didn't really exist at all. Nowadays, it runs on everything that matters, and although it has been really dormant for quite a while, it has a much more complete APA coverage than the SSL module in Python 2. And what's even more important, in the past month, it got a really new vigor thanks to the PyCA cryptography library, which is a crypto library without footguns. It's been written by some rather smart people, and eventually the Python Cryptography Authority, or PyCA in short, formed around of it. And a side product of that are PyPI-friendly CFI bindings for OpenSSL. And they're probably, we are working also on other backends, so secure transport is in the works too. And what's important here is that it gave PyOpenSSL some serious momentum, because they could just throw out all their gnarly old C code and concentrate on building Python abstractions on top of the bindings that are provided now by the cryptography library. So, which, in other words, PyOpenSSL is now a pure Python library. What's unfortunately still missing is hostname verification. Again, on PyPI there is help. Service identity gives you a hostname verification and some other more obscure ways to verify the identity of a service, which probably no one of you ever heard of. You will probably never use it, but it's in an RFC, so it's implemented. But again, double opt-in, you have to think, remember to use it. So, let's have a quick look at common frameworks and packages. Yeah, they are pretty bad, all of them. So they are all using the standard library, so Tornado could do better on Python 3, but they don't. So who's doing a bit better here is Twisted. It took me a year to get those check marks there. So yeah, you have to use Twisted 14. It has been released like 3 weeks ago or something. But yeah, on the server side, the story is more or less complete. The only thing that's missing is SNMI. What's also okay is MicroSG, because the thing is they, despite a convincing name, they are not Python specific, which means they just went on and wrote their own some C code, which I personally find highly suspicious. I don't trust C code that uses SSL that has not been widely reviewed, which is not true for MicroSG. So I would still always put them in Nginx in front of it. So, and as long as those libraries will keep using the standard libraries SSL module, these daggers are gonna stay. There's no way they could. Well, there is one way, but we will see later. So, client side, still terrible. You can do slightly better, like Tornado. They just depend on the verification callback, the verification backport, and certify. Or at least the next version will depend on certify. The current version has a slightly older version of certify packaged hard in, but yeah. So, Twisted is a bit more complicated. The low-level functions are all there, so you can write secure software if you want to. The HTTPS agent, which is the higher level HTTP library, does the right thing, and by extension also the track library, which is kind of a port of the request library for Twisted. And yeah, the only thing that is missing is a proper TLS endpoint that does the right thing when you connect to hosts, but I'm confident that that will follow this year. But it is possible to write secure software since 14.0. Again, 14.0 is the TLS release. So, what's never going to be useful is standard libraries. URL doesn't verify anything, you can send anything don't use it ever. If you have to open HTTPS URLs, of course. Use requests. Don't think that request is great because of the nice API. We all heard of it. But what I like even more is that it really goes a long way to do the right thing. It's use urllib3. And if you install PyOpenSSL and some other modules, you get really the very best TLS support you can get nowadays. So, oh my god, it's too late. Let's sum up. Keep TLS out of Python if you can. Use requests for HTTPS queries. Make sure you're using the PyOpenSSL backed one. Write TLS servers in Twisted. And if you need low-level TLS, which you should avoid, use the latest version of PyOpenSSL. It has much better coverage of OpenSSL APIs on Python 2, and it will follow you to Python 3, if you ever pull. So, use the Python 2 standard library only for clients and only if you have to, and whatever you do, use the correct backports to verify. So, I'm just going to sum up now. So why is the state sorry? It's sorry because people still say SSL, although it has been obsolete for 15 years. It's sorry because implementations are terrible. All of them. It's sorry because users run outdated software, click certificates warnings away, and are at the mercy of third parties. And those third parties let them down regularly. Servers run completely outdated software that is configured completely poorly. Clients don't verify anything, although it's their only job. And we're not talking about some obscure freeware here. Security researchers from IOActive found 40% of online banking apps vulnerable to MITM attacks. So, and finally, it's sorry because Python is at the forefront of being terrible. The current state really is sorry. The title is not really attention bait. However, there's hope. So first of all, people started caring again. So this is always the first step. Every alcoholic will tell you, acceptance, and then the rest will follow. Standard library support got much better in Python 3.3. And if you ever needed an argument for Python 3, there it goes. But even for Python 2.7, Nick Colan is working on a tab to make the SSL module slightly less shitty. So there goes your argument for Python 3 again. And I've already mentioned the Python Cryptography Authority. It's a bunch of really smart people, plus me. And we've already adopted several crypto-related projects. So ultimately it should become a single stop for solid crypto software for Python. And this is a really huge deal because the standard library simply moves too slowly to respond to the pressing issues of security. But help also means work. So, stop believing that a log icon makes you and your data safe. Don't click away certificate warnings. Do not install root certificates. Be a critical user. Configure your servers properly. Install security updates immediately. When you connect to a server, verify all the things. Verify the trust chain, verify the hostname. And finally, help us to get Python out of this mess. Fix your libraries. Fix your software. Report bugs to upstream. Help upstream fixing these bugs. There's really a lot to do. I did a short survey of the Python TLS landscape while I was working on this talk, and the results were rather discouraging. Yeah, and that's all I have for you today. So I hope you learned something today, and more importantly, are eager to fix. So go out, study the talk page, follow me on Twitter, and get your domains from Media to speak German.
Thank you, Hynek, for such extensive and deep dive into security. Any questions, guys?
Thanks for the talk. I have a question which might be a little bit off topic, but well, anyway. What's the current state of running TLS over UDP? UDP? Yeah, just UDP.
there is DTLS, I think is the name of it, but I've never used it. It's not really relevant, so I'm not sure if there's any wide deployment of UDP. Maybe BitTorrent?
WebSockets use DTLS or something.
Yeah, but no idea. Sorry.
Okay, thanks.
No, WebSockets WebRTC.
Any more questions?
Have you ever met a case when there's too much security and, for example, the valid certificate is just thrown away or I don't know, accepted to be unsecure by the client, by browsers, but it's actually invalid, just some, I don't know, well, do you solve such cases where too much security for checking certificate was applied?
I'm not sure I understand the question. Sorry.
I saw use cases, for example, for Android, where a valid certificate, which almost all other browsers are accepting, the Android, for some reason, just does not accept this certificate because there is an error in somewhere in the chain or something like that.
Yeah, I think I understand what you mean. I think right now we are in a sort of a transition period where people start fixing their software and they realize that a lot of things are broken. So like people add hostname verification to their clients and suddenly they realize that the hostname certificates were wrong all along, or that their servers are poorly configured and that they the only thing that's semi-likely to happen with certificates right now is that the CA started to roll out SHA-2 certificates like I have, which is pretty cool, but they are supported only from Windows XP Service Pack 3. So that's probably one of the most likely things that can happen when you have too much security and the client can't handle it. Other than that, there's really a lot of really bad software when it comes to cryptography, so it's possible that the certificate was okay, but the software parsed it wrong, or there's a lot that can really go wrong, it's true. And as I said, this is really a transition period, and as we keep fixing things, more problems will pop up. So you have to test, that's the point. You have to always test your deployments because there's so much unexpected mistakes.
Okay. More questions?
Thanks for the talk, and a kind of strange question. Is there any point in having an additional security after you terminate the client TLS? For example, between your Jinx and your Python backend, because you know clouds and stuff, you don't really control the infrastructure.
Yeah, so that was part of my talk last year at PyCon. So where I work, we have real servers in a real computer center, and we still use TLS for everything. Because as soon as you have, for example, customer servers within your network, they are just one root exploit away from sniffing your network. So it always depends. You have to decide it for yourself, but we definitely go TLS by default. So we also send our backups around with SSH, and so because you never know. And in a cloud, it's, of course, you have even less control in a cloud. So we have the luxury that you plug our own cables, but you don't know what's going on in some Amazon center. So
When you say 2 words about certificate pinning. Is it a good idea?
Pinning?
Yeah.
Oh, pinning is a great idea. So I think Armin will talk about that a bit too, because he's a big fan of not using trust databases, but to use our own certificates and he pins them. It's not something you can always do, but if you're, for example, shipping an app and you have a backend server, then it totally makes sense to pin the app, to pin a certificate within the app, so you know what's going on. You should totally do that if you're a bank, for example. So, or you can at least pin the CA, which the certificate should come from. So, for example, if you're only having Komodo certificates, might be easier to pin to them. So, if the Department of Defense of the United States of America issues a certificate for your host name, then you will know.
More questions?
One more thing. There's one thing. You can pin certificates using DNS nowadays, right? But nobody uses that. It's this DANE, D-A-N-E. Maybe it will be a bit more, will get more traction now, because it's a really interesting concept, because you have to double check stuff. Okay.
Last question.
Thank you so much for such interesting presentation. So, 2 questions about your slides. On one slide you have a table which you show that Tornado is pretty good in TLS and other servers are not, and you had a graph FPS. Maybe I missed something. What's FPS?
So first of all, I said Twisted is really good for servers, not Tornado.
Twisted, sorry.
Wait, I just get
PFS something.
PFS, yeah, perfect for secrecy. That's the thing that if an attacker gets the server key, if the connection has, so, okay, assume heartbeat, okay? And someone steals your secret server key. If your connections are done using RSA key exchange, this attacker can decipher the text that he's capturing there. If the connection has been done using DHE or ECDHE, they can't, because the encryption keys are determined in a different way. So, and this property is called perfect for secrecy. But the secrecy or the confidentiality of the payload is not dependent on the secrecy of the secret server key.
Okay, thanks. And just another question about another slide. You said that TLS doesn't provide end-to-end security. What does it mean? End-to-end security.
Thank you. That's the example I gave there. So if you're chatting with someone over Jabber, for example, so and you are connected using TLS with the best possible encryption to your Java server. That's the direct peer security. That is what TLS gives you. But TLS does not give you security until the other person you're talking to. So the confidentiality or security of this whole conversation is not determined by the TLS, because the TLS is only the first part, and there are more steps until the person receives what you've written there. So this is end-to-end encryption, like PGP, because you encrypt it on your, then you send it however you do, and the recipient deciphers it. But if you're writing TLS, it's the intermediate server that deciphers the TLS you're writing. So.
Thank you, Hynek.